cryosphere in the past. The most recent ice age occurred roughly 20,000 years ago. This is the ice age that we often refer to as the Ice Age. This ice sheet was up to a mile thick in places over Canada and the northern United States. There were great changes in climate which followed the melting of this ice age, such as sea level rising dramatically. The greatest ever ice age that we know of occurred roughly 650,000 years ago. The ice sheet spread from the Hudson Bay in Canada all the way into the Midwest. It also spread deep into Germany from the center of the Scandinavian Shield. In this period, the sea level dropped by 400 feet, and the overall global temperature plummeted to 5 degrees Celsius. Though the most recent glacier did not reach as far south as Virginia, our area has still been influenced by small mountain glaciers. Though the Appalachian Mountains were formed by converging continents and volcanoes, it was the glacial activity which followed that shaped the region. The types of glaciers that have been active in carving out many different features in the region, the first being cirque glaciers. These type of glaciers form in small hollows and slowly compact to form a block of ice. The second type of glacier is a valley glacier, which flows down a valley which may have been previously carved out by a river. Glaciers have shaped the landscape of many regions all over the world, including the Appalachian region, leaving behind a wide variety of features. Glaciers do this through different types of erosion and deposition. Glaciers are very powerful masses and can easily break away huge chunks of rock. This can leave behind features such as U-shaped valleys, hanging valleys, ribbon lakes, and quarries. U-shaped valleys are what is left behind when a valley glacier melts. They are formed as the glacier erodes the bottom and sides of the rock it flows past. The rock surrounding the glacier is eroded by processes such as plucking and abrasion. Plucking is when melted water freezes and fixes itself on the rock. The glacier then moves and a large chunk of rock moves with it. This process can break off some significant chunks of rock. This rock is then carried in the glacier and can rub against the floor and walls. This process is known as abrasion and also aids in carving out this large U-shaped valley. Hanging valleys form when a tributary glacier flows into a large main glacier. As the tributary is smaller, it does not erode as deeply. This means that when the ice melts away, the valley is hanging above the main valley. Often there will be a waterfall which falls from the hanging valley. Ribbon lakes are long, thin lakes, which are generally found in U-shaped valleys. They form when the glacier hits a patch of softer rock. It erodes this rock more, leaving a dip in the land when it melts. This dip is then filled with water to form a lake. The lake is long and thin, as the trough which is eroded out is done so while the glacier is moving. Quarries are large hollows in the land, usually high in the mountains, with two side walls and a back wall. This is where a cirque glacier has formed. The hollow began as a small depression, but over time has been eroded much deeper. Over time, the ice has plucked and abraded the back and side walls to get deeper and deeper. Once the ice is melted, a hollow is left behind, which is often filled in with a lake. At the front of the quarry, there is often a rock lip, which is where the glaciers deposited material as it began to flow downhill. Glacial erratic are boulders or pieces of rock which have been deposited in strange places. Often these boulders are far too large to have been transported by a river, and so must have been left by a glacier. They also sometimes don't fit in with rock types in that area, so have clearly been trapped or transported from another region.
The present. Global climate change is the long-term change in average weather conditions, including temperature, precipitation, and wind. According to the UN's IPCC, our climate is going through startling changes due to the release of greenhouse gas emissions caused by human activity. The cryosphere is warmer than it used to be and continues to get warmer. This Arctic warming is generating changes to ice cover, sea ice, and permafrost in the Arctic. Data from satellites show that over the past 30 years, sea ice cover in the Arctic has decreased by 30%. Also, snow cover on land in the Arctic has declined, and the frozen ground in the Arctic region has also started to thaw. The Arctic climate is detrimental to the rest of the planet because it gives off more heat to space than it absorbs, which helps to cool the planet significantly. This is why changes in the Arctic climate could have damaging effects to the climate for the rest of the world. Researchers stress that these changes in the Arctic are troublesome because they could cause feedback effects that prompt further warming. An example of this would be when sea ice melts in warmer seasons and spaces of darker water are exposed, which could cause more absorbing of heat from the sun and then release the heat into the atmosphere. Melting permafrost in the cryosphere releases even more greenhouse gas into the atmosphere. The warming of the planet has caused soils in the polar regions that have been frozen for as much as 40,000 years to thaw. As they thaw, carbon trapped within the soils is released into the atmosphere as methane. This methane causes warming to continue, which then melts more of the frozen soils. Scientists call these positive feedbacks occurring in the Arctic regions Arctic amplifications. However, some changes could also potentially cause negative feedbacks that can help to reduce the amount of warming. However, nearly all evidence advocates that the positive feedbacks outweigh the negative, and the recent report done by NOAA has decided that the Arctic climate is probably not going to be able to return to its previous conditions. The global effects of climate change are already apparent in the rapid melting of glaciers and thawing of the permafrost, changing precipitation patterns, and a rising sea level. Regionally, some of the changes are already apparent and include more frequent flooding of low-lying land by storm surges. Ice sheets have caused the mid-Atlantic lands to bulge upward, and removal of the ice is causing the mid-Atlantic to sink. This has resulted in current rates of relative sea level rise roughly twice the global average. The Virginia Institute of Marine Science did a report on a recurrent coastal flooding and used 4 scenarios of sea level rise for planning purposes. The scenarios were developed and modified for southeastern Virginia by incorporating an estimation of land subsidence in the region. The scenarios represent possible courses for local sea level based on a combination of factors. The lowest or historic scenario is an estimation of observed long-term rates of sea level rise that goes back a century or more and includes no acceleration. The low scenario is based on conservative assumptions about future greenhouse gas emissions. The high scenario is based on the upper end of projections from models using statistical relationships and global observations of sea level and air temperature. The highest scenario, or worst case scenario, is based on estimated consequences from global warming, combined with the maximum possible contribution from ice sheet loss and glacial melting.
The future of the cryosphere. Glacial ice deposits have been declining at increasing rates throughout the last half of the 19th century. Although glaciers have melted periodically over the last 2,000 to 3,000 years, no circumstance compares to rates following the industrial era. Scientists predict that current depletion rates will only sustain or accelerate throughout the 21st century. If current patterns of climate change continue, Earth can expect a nearly ice-free Arctic by the year 2030. As global temperatures continue to rise, mass that was once stored as ice at the Earth's poles melts and flows towards the equator due to Earth's rotation. This transference of mass from the poles to Earth's equator is also known as glacial isostatic adjustment. This occurrence causes the lithosphere to morph as compaction from ice sheets releases with glacial depletion. As compacted crust at the poles slowly rises, crust in lower latitudes slightly sinks, which has the ability to increase land subsidence in certain areas and even alter Earth's gravitational field. However, this change in the lithosphere is minimal compared to the rate at which water is being added to the oceans. As glacial depletion accelerates, sea levels will continue to rise and the potential for larger and more frequent storms will increase as well. This rise in sea level is beginning to affect coastal communities all over the world, but some areas are more susceptible than others. Virginia's Hampton Roads region is currently the second most threatened region in the U.S., and sea level rise is largely perpetuated by land subsidence. From 1930 until present day, sea level for Norfolk, Virginia has risen nearly 1.5 feet, and the current flood barrier is being breached much more frequently. Flooding in downtown Norfolk is becoming much more common, and matters are only expected to get worse as the Virginia Institute of Marine Science predicts that sea level for Norfolk will rise another 1 to 2 feet in the next 20 to 30 years. The Hampton Roads area consists of 13 communities and is home to nearly 2 million people. It is estimated that sea level rise threatens up to $3 billion worth of property and infrastructure. This has captured the attention of the U.S. military because the region is home to the world's largest naval base and gets 46% of its economic wealth through spending by the U.S. Department of Defense. This has caused the U.S. Department of Defense to begin working with local governments to address future impacts. In July of 2014, the mayors of Norfolk and Virginia Beach met with U.S. Senator Tim Kaine to discuss how they would address sea level rise in the coming decades. Officials all agreed that they must reduce greenhouse gas emissions in order to combat climate change. However, reducing emissions will only help slow effects of climate change in the long term and will not be enough to prevent inevitable changes that will result from damage already caused. Officials have begun planning adaptations and are estimating that Norfolk will require a budget of nearly $1 billion to replace current infrastructure and keep the water where it is. Other groups like the Hampton Roads Adaptation Forum are working with local governments to incorporate new plans of design for communities that are threatened by sea level rise. The forum consists of local, regional, state, and federal agency officials, as well as engineers, city planners, and academic institutions. Together, the group aims to inform communities and share knowledgeable ideas that can accommodate infrastructure with changes in Virginia's coastline.